Hello everyone. So today I'm going to talk about some side notes about boundary condition types that you should be familiar with in order to solve these PDEs that we talked about. And after that, I'm going to um solve one example and kind of the final example for finding characteristic curves in nonlinear PDEs and how you should approach those kind of problems that are kind of more complicated than the linear ones that we solved so far. And after that, after this lecture, we're kind of done. We will be done by the characteristic curves, and from next lecture, I'm going to talk about Sturm-Liouville problems and another method for solving these PDEs, that is separation of variables. Okay, so let's get started. So there are three types of boundary conditions that you might be given in any of these PDEs when you see these PDEs. So let's see what are those. First is what we call Dirichlet or first order first type boundary condition. Okay, so let's see what it is. So here in the first type, you specify, this is the simplest case, you specify U or a solution along a specified boundary location. Okay. So let's see an example that how does this look like. So for example, if you have something like this, a boundary, a domain of where you want to investigate as this, okay, and this is your omega domain. This is the domain that you want to solve any PDE. So this domain can you can specify the solutions in different parts of the domain. Okay, for example, the first part we can say up to here. This region, I'm gonna say I have a boundary condition partial gamma 1. Okay, and then you can do it differently, right? For any boundary you can do it. So here up to here you can say I have like partial gamma 2, and then for this region you can say I have partial gamma 3. Okay, so let's say here you have gamma 1, gamma 1, gamma 2, and gamma 3. Okay, so this is the boundary. Okay, so this is the boundary, and you have to specify the boundary condition over this. Okay, so the first boundary type, boundary condition, or Dirichlet boundary condition, simply says that you need to specify a solution along a specified boundary location. Okay, for example, you can say U along gamma 1, partial gamma 1, omega 1 is gonna be a given number, right? So it could be a U given. You can specify that, okay? So this is the first type of boundary conditions. Just one side note that if u given is 0, then we say that the boundary condition is homogeneous. Okay, so this is just nomenclature. So this was the first type of boundary condition, or what we call Dirichlet boundary condition. And now let's go to the second type. So I want to talk about the second type. So the second type is Neumann or Neumann boundary condition, or second type boundary condition. Okay, so the first one was Dirichlet, second one is Neumann. And for Neumann, what we do is we specify instead of u itself, we specify its derivative. We specify normal derivative at a given boundary, or at a specified boundary location. So normal to boundary. So for example, if you have the same thing here, let me just redraw it. Okay, something similar. And then this is the domain. And say we have divided it again similarly. So for the second one, what I can do is again, these are just some example, and it could be more complicated. You can have like tens of these divisions, or it can be just one. Like it can be, you can just first type boundary, like gamma one, or you can you can have much more than that, like many of these divisions. Okay, so this is just example for illustration, so you get the idea. So for example, for the second one, what I can do, so for the second one, we need to specify the normal. So the normal derivative. So say this is, if this is the normal vector, and you can have it everywhere, right? So just quickly show it. This is going to be the normal vector to the boundary, right? So how the way you define it is specify the normal derivative at that location. So what I'm gonna do is this. I'm gonna say partial u partial n, which is a normal vector to the boundary, at gamma 2 omega 2, or this can be also written in terms of the divergence. So you take the divergence of your vector, your velocity field or u field with the normal vector. This will be a given number, okay? So you can say along this, let me just show it here, like with this, along this line, along this part, okay, we can say along this part that we know that normal derivative, okay, we know the normal derivative of u with respect to the normal vector. and this is a given number. Okay, so this is what the Neumann or second type boundary condition looks like. And I just want to give you a note that given a standard flux law, for example, Darcy law or any other flux law, this boundary condition corresponds to specification of the normal flux. So this is very important because and it's used a lot also in, for example, fluids phenomena. For example, you want to say you have a zero stress boundary condition. Stress in fluids is you need to take a derivative, right? So this is how you can set that zero stress boundary condition with this Neumann or second type boundary condition, right? And or another example could be like in heat flux. You can say you want the heat flux going out of a boundary to be zero, right? So the way you can set that is to say that, for example, your D temperature, dN should be zero along that. So this means that you don't have any temperature flux, and the temperature here and here should be equal, but it shouldn't be necessarily equal to like here, right? So this could have another temperature, but along these lines, along the normal vector, they should be equal, right? So this is what this means, and this is your normal vector. So this is very important boundary condition that is also used a lot in numerical analysis, especially when you want to set a zero flux or zero stress boundary. And then the third one is a combination of these two. So this is what we call radiation or third type boundary condition. And what it is combination of one and two. And that means that we specify both u itself and its normal derivative at a specific location or a specific boundary location. So for example, you say alpha u plus beta partial u over partial n at specific boundary location. We can say omega 3 equals to gamma given. Okay, so this is the third boundary condition. So for example, here we can say that for this region, we can say we can just specify this boundary condition here, right? We can say that the boundary at omega 3 should satisfy this equation. Okay, so this is the third type of equation or third boundary condition. Okay, just a final note here that for the Laplace equation, which is the Laplacian of u equals to 0 for x and y belonging to omega, which is our domain, we cannot specify only second type or Neumann boundary condition along the boundary. And you can investigate it yourself. So as a practice problem, you can explain why this is the case. And it is, as you see, because of the type of the equation that you can have multiple solutions, right? If you just specify this like the Neumann boundary condition for a Laplace equation. So we want to have a unique solution, and so that could be that can be why this is not the case. Okay, so as a practice problem, explain it why, and this is kind of the summary of the boundary conditions that we are going to face mostly in this class and in general in most engineering problems. Dirichlet or first type boundary condition, where you just specify your solution along a specified boundary location. Neumann second type boundary condition, and which is where which you specify the normal derivative. And third one is radiation or third type boundary condition, which is just a combination of the first and second one.